All right, so I'm Mattias. I'm gonna talk about web streams today. Don't know if you've heard. If you haven't, great, because I'm gonna talk all about web streams. So, first off, little introduction. So I'm lead software architect on THEOplayer. I am also a co-editor on the WhatWG stream standard that is speccing this streams API for JavaScript. And I'm also the maintainer for the polyfill for this API. So I brought a bit of baggage. I'm very happy that I can talk about one of my favorite things in the JavaScript land. So first off, web streams. Has anyone actually used web streams yet? We have a couple. Those are the TO Live guys, so I expected that. Okay, so it's a fairly unused, a bit of an obscure API, but it's really powerful, so I'm trying to convince you today that it is maybe something you want to try out. So, first off, what does MDN have to say about the Streams API? Well, it says that it allows JavaScript to programmatically access streams of data received over the network and process them as desired by the developer. I don't know, that doesn't say a whole lot to me. So what is a stream in that sentence? What can you actually do with this API? Well, a stream is, first off, an ordered, possibly asynchronous data flow whose chunks can be read, processed, and written in an incremental fashion. That is a huge mouthful, so I'm going to break that down for you. First off, it's ordered. So this data flow, you have to process the nth item before you use the before you get the n+1th item. So it's like an array. You have a fixed order. You can't look into the future or look into the past. It's possibly asynchronous, so the next item might not be available immediately, and you might need to await a promise. This is something that you don't get with arrays. Arrays are fully available immediately. It's a data flow of chunks, where a chunk is actually arbitrary data. You can choose your chunk type. You can make a stream of strings, you can make a stream of numbers. You can also have byte streams, where your chunks are arrays of bytes, usually a uint8 array. And those are show up frequently when you're dealing with network or files. It can be read, processed, or written, so you have different kind of streams, whether you're a producer or a processor, a transformer, or a consumer of the stream. You might interact with the stream in different ways, so you get different kinds of streams. And lastly, you all do this in an incremental fashion, so you can start processing before the entire data is available. You don't have to buffer all of the data in memory before you can start doing useful work, which is something that you usually don't have with arrays. Or regular values in JavaScript. You usually get the entire thing all at once, and it has to stay in memory the whole time. So, why would you need streams? Well, as I said, you might need to process a large amount of data that doesn't fit in main memory, in main RAM. So, for example, you might want to do a full text search over a large quantity of data, like the entirety of Wikipedia, which I looked this up actually. It turns out if you compress Wikipedia, it only takes up like 22 gigabytes, and we have RAM that big these days, so this might not be applicable anymore. Like, computers just are getting faster and bigger all the time. But something that you definitely can't do is process uncompressed full HD video, which still nets you at around 9 gigabytes per minute if you try to do that for full images. You can't keep up with this with any regular computers. So you have to do this streamingly. You can't buffer the entire video. Something else you might want to use streams for is if you want to serve content before the entire page is loaded. You see this pop up with React server-side rendering, where you can these days have suspense things in your components where the data shows up later. It's being loaded on the server and it's being streamed to the client while the page is rendering. And that actually uses streams under the hood. What you can also might want to use streams for is very relevant to what we are doing at Theo. We want to start playing your video as soon as possible, before without having to load the entire video file at the client. So as soon as we have a couple of video frames, we want to start playback immediately. And you need streams to do that at the very lowest of latencies. So let's get into it. Our first kind of stream today will be readable streams. And as the name implies, you can read from this readable stream. It is a source of data, and that gives you chunks. Now, a readable stream can only be read by a single consumer at a time, and that consumer is usually represented by a reader. So first, you get your stream somehow. That is your const readable. You get a reader of it, and that locks the stream to that reader. And then you can start reading from that stream. So the API for that is reader.read. That returns you a promise for the next item. And there's two things that can happen. Either you get your item, there is still something in the stream, and it has just become available. And so that is line 11. You'll get your chunk, and you can do something. And here we're just logging it to console. The second thing that can happen is that you've reached the end of the data. There is no more data coming in, and done will be true, and you can just stop your consumer there. That is the basic use of a readable stream, just looping over all of the chunks. Where can you use this? Well, for example, if you've used the fetch API to make HTTP requests and getting responses out of that, what you usually do is use the response.array buffer or the response.text method to get the entire response data as an array buffer or as a string or as a JSON object. That buffers the entire response and then gives you the entire thing in one go. If you want to do useful stuff while the response is being downloaded by the client, if you want to get into what is coming in from the network while it is being downloaded, you can use a stream. So instead of using array buffer, you can use the body property to get a readable stream of your response. And again, you can loop over the chunks coming in, but now you get each chunk separately as it's coming off the network, which opens up a lot of interesting applications. Now, you don't always need to have your streams coming from an existing web API. You can make your own. So the readable stream is constructible. You give it an object where you can specify some methods on how you want your stream to behave. So the first thing that happens is that your start method gets called and you get access to a controller. And this controller is what you use to do useful stuff with your stream. When more data is needed from your stream, the pull method is called, and then you can hopefully set something up that will eventually put more data into the stream. And when the consumer is no longer interested in your stream, maybe something else happened, maybe the user clicked a cancel button somewhere, or maybe they navigated to a different page, your cancel method gets invoked and you can clean stuff up. Now, again, this controller gives you ways to modify the state of your stream. So what you usually want to do is enqueue more data. You somehow get some more data that belongs to your stream. You enqueue it and it'll get to the consumer. When you reach the end of your input, when you no longer have any more chunks that are gonna come in, you just say controller.close. That closes your stream normally. If you encounter an error while you're trying to get more data, you can say controller.error, and that will abruptly close your stream. So the consumer will get notified that there's an error, and they can clean stuff up on their end too. So how can you make a stream? One way would be to do a push source, which is where you get events coming in and you just push them onto the stream without caring whether there is a consumer waiting for that data or not. So an example would be if you just record every click that happens on the page and you put that onto the stream. And a consumer can then read the stream and see all of the times where the user has clicked on the page. So here in our start method, we just set up our listener. In our listener, we're going to enqueue every click that happens with the X and Y coordinates of that click. And then if the consumer is no longer interested, we can remove that listener, make sure that we no longer push any more data onto the stream, and then we're done. Another way of writing a stream is a pull source, where you make sure that you only start requesting data when a consumer is asking for it. This is a bit more efficient, because otherwise you're just piling up data in memory that is not being used. So for example, if you're doing something like a paginated infinite scroll, so you have your users scrolling through a timeline of blog posts, and when they reach the end of the list, you load more data, you load in the next page immediately afterwards. So here, the pull method is only called when the reader needs more data, and the stream will wait for your previous pull to resolve before it calls your pull method next. So you can be sure that there is only one fetch happening at the same time. So here we just fetch the next page, we parse it as JSON, we enqueue all of the posts from our API onto the stream, the reader can read those, and then we're done. We can wait for the next pull to happen. Now, an issue with streams is that you can only read them once, and this is something that users can trip up on. They expect that they can reuse a stream as many times as they want, but actually every chunk that you read is coming off the stream, and it no longer has to be in memory for that stream. It's considered consumed, and that is what makes streams efficient, because otherwise you can buffer things indefinitely and you'll eat up all of your RAM. So what happens here, first we read through the entire stream with our first reader, and then when that's done, we try to use the next reader to read through the stream again. But the stream has already reached its end at that point. We've already gone through the if-done break, so the next reader will just do if-done break again. And there's nothing useful coming out of reader 2. So a solution there would be to tee your stream. And teeing takes your stream and turns it into 2 streams. And both streams will get the exact same data coming from the original stream. So here, the first loop will be using body 1, which is a stream that has all of the data coming in. But while you're using the first reader, the second stream will keep all of the data ready for the second reader to consume afterwards. Now, that was readable streams. On to the next kind, which is writable streams. This is kind of the reverse. So where readable streams is something where you can read data from, writable stream is a destination where you can write chunks to. One useful usage of this would be the file system API. So this is an API in web browsers that allows you to open a file and then open it for writing some data out of your app to the file system of the user. So first you do show save file picker to get a file. The user will get the save file dialog. They'll say, okay, I want you to write it to this file, and you'll get a file handle back, which you can call create writable on to get a writable stream. And it's kind of similar like a readable stream. You, instead of getting get reader, you do get writer, and that gives you a writer, which locks the stream again, so you're the only writer that can use that stream at that time. And you call write to write data to the stream. And when you're done, you call close, and I'll close the file and make sure that it's written in its entirety to the file system. Now, creating a writable stream looks very similar to a readable stream. So again, you have your start method. Instead of pull, you have write, which gets you the chunk that is being written into your stream. You can then decide how you want that to be processed, where you want that chunk to go. When the writer is done writing chunks, you get a close call, and if the writer encounters an error, if something happens while producing the content of the app that wants to be written to the file, you can say, okay, abort it, don't actually write to the file system or whatever, just clean it up right now. Now, very simple example would be to just log every chunk that is being written. You can do more fancy things like putting it into the DOM somewhere, putting it on your page, but this is useful enough for an example. Now, where things get interesting if you start combining readable and writable streams. So a readable stream is something you can read from, a writable stream is something where you can read to, and a pipe to is what takes everything coming off a readable and writes it to the writable. You don't have to write this loop every time yourself, you can just call .pipe2 to make that happen for you. This also propagates closing, so if the readable reaches end of stream, writable closes and makes sure that the file is written in its entirety, and if any of the two encounters an error, the other gets the error too, so that they can all clean up properly. Now, this becomes very interesting if you use it together with a transform stream. What is a transform stream? It's actually two streams. So you get a writable and a readable stream, and data that is being written to the writable stream is then transformed in some way by the transform stream and made available to the readable end. So again, API looks very similar. You get your start method, but this time you get a transform method that is being invoked. Instead of the write method from a writable stream, you can transform the chunk being written to the writable end and then enqueue it back onto the readable end with controller.enqueue. So this is where your transformation happens. You get a chunk in and you can do something with it and then enqueue it back to the readable end. Flush is basically your close method from writable, so that will make sure that your readable end also gets closed, or you can still enqueue some like suffix chunk if you want in the flush method itself before you actually close the stream. And cancel happens when either the readable gets cancelled or the writable gets aborted. Now, how do you use a transform stream? Well, I said it's two streams, so you use the APIs that work for readable and writable. So you have your input somehow, you have your output somehow, you have a transform stream. This one just changes all of the strings in the stream to uppercase. So first we take our input readable stream and we pipe it to the writable end of a transform stream. So that is line 10. Then on line 13 and 14, we take what is coming out of the readable end of the transformed chunks out of the transform stream, and we pipe that to the output writable stream. Now, because this is something that that happens so many times, the Streams API has a shorthand for it, and we call that pipe through. So pipe through will do both pipes. It'll pipe the input to the writable of what you give it, and then it returns the readable so that you can pipe that back to the output stream. So that makes things very easy to write, and it also makes it very easy to compose. So if you have multiple transform streams, you can do pipe through, pipe through, pipe through, and then eventually pipe it to your final output. And so this is what really takes advantage of all of the Streams API and what you usually would write as your like top level application code, where you set up your entire like long pipeline, your long pipe chain that does all of your application logic. Now, a bit of a more advanced topic. So what Streams are also doing in the background is queuing chunks that have not been read or written yet, and also managing back pressure for you, which is also really important to get really efficient streams. So every stream has an internal queue. So for example, if you have a readable stream where the reader is not reading yet, you might have your source and queuing chunks that are not being consumed immediately, so they go into queue. And so if a reader comes along later, they can get it immediately out of the queue and then catch up with the source again. The same thing happens with a writable stream. If you have your writer pushing in chunks in too fast before the sync can deal with them, they get into the queue and then you can process them later. And a transform stream, it's again a pair of streams, so it has a pair of queues, one for the readable and one for the writable end. Now, you can have your stream. Your stream will try to fill up its queue to up to the desired stream, up to the desired size of the stream's queue, and that the specific size of that is governed by a queuing strategy. So, for example, you might have a strategy that says, I want to keep around 10 items in the stream's queue, so that when a reader comes along and is not being very fast at reading, we try to fill up to 10 items, and then we stop requesting more items, so that a reader can easily get some items out quickly. But then if they're but then if they're no longer asking for them anymore, we just stop at 10, and then we wait until they actually start pulling things out of the queue. That is important to keep your queue sizes bounded by some number, so that you don't again fill up entire main memory just because you're just not using your data immediately or fast enough. So a count queuing strategy is just doing that, counting the chunks in your queue. There's also the byte length queuing strategy, which counts the number of bytes in your byte stream. So if you have chunks coming in with various sizes, this will add them all up and then see what is the total size of your queue to keep that bounded. So for example, this example stream here, it'll stop pulling at 10 calls to pull, and then it'll just pause until a reader comes along and starts using the chunks. Now, back pressure is when your queue size exceeds the desired size. So the readable stream will stop calling pull. It will no longer request more streams off the main source. And a writable stream, when it reaches its queue size, it'll say to the writer, I'm not ready to accept any more chunks at this time, so please hold off with calling write if you can. And in a long pipe chain, so again with lots of transform streams in the middle, this back pressure signal will propagate from the back of the stream of your final sink all the way up to the original source readable stream, usually a fetch or a file that you're reading at the front. And then that helps make sure that you're not pulling in too much data off the network that you're not immediately going to use. So when you encounter that, you want your original source to try to deliver chunks at a slower pace, so that we don't again consume the entire memory. Okay, now that is all readable, writable, and transform streams. There are some cool new features coming up in the Streams API that you might want to start using. So one thing that we've seen coming up again was this reader loop. You always had to write while true, await reader read, and then check if it's done, and then do something. This is boilerplatey, and it's annoying to write, so I'm happy to say that you can now just write for await off. Yes. So for await off, this is like a for off loop, but it has the await built in. So not only can you iterate over regular arrays or sync iterators, you can also iterate over async iterators, and a readable stream is an async iterator. It implements that protocol. So it makes writing consumers much easier. And it's actually being supported pretty well now. Firefox had it since version 110, and since Chrome 124, which released in April, you can also use this in Chrome. Now, there's also the inverse, readablestream.from, which makes it easier to convert any data that you already have and make it a stream, make it into a readable stream. So usually you start off maybe with just a fixed array of chunks, or maybe you have a set of chunks and you want to turn that into a readable stream, or maybe you have an async generator function that is somehow generating your chunks, and you can also turn that into a stream, all with the same API. Or maybe you're using this in Node.js, which also implements the WebStreams API, and you can take a node readable stream, which is a different API, but it also implements the async iterator protocol, so you can convert that with readable stream.from into a readable stream. So this makes interoperability really nice. You can convert basically anything into a readable stream and then iterate over it with 408 auth. You don't really have to worry about what kind of data you're dealing in, what kind of format it is. You can convert back and forward, however you like. Support is not great yet, so Firefox is doing a really good job here, but Chrome needs to catch up, and Safari, well, yeah, the Apple guys over at Cupertino really need to get to work with streams, but it'll come. Now, streams is great to process data that is coming off the network, but you're still processing it on the same thread. So you get you do your network request. The browser is usually doing that on a separate thread, but then you still hit main thread to do your actual processing with it. Whereas if your processing is like really CPU intensive, you might not want to do it on your main thread, all of your work, but then still eventually like get the final result of your final stream onto main thread and then do something with it. So the way you would do that is transfer your stream to a worker. So if you've used web workers before, you might know about the post message API. What you might not know is that a post message API also takes in a list of transferable items. So the second parameter there, that says that these objects, I no longer want to be using this in this context, on this thread. I want to transfer ownership of this object to the other thread. So here we use that to set up a stream, a pipe chain across threads actually. So on the main thread on our page.js, we make a transform stream. We keep the writable end on our side, but we say, I want to transfer this readable end to the worker. So I can use the regular getWriter API to write chunks on main thread, put them into the stream, and they'll magically appear again on the other side in worker.js in its readable view of that stream. And so you can use this to do CPU intensive processing on another thread. So here we're again using a worker. This time it is the worker posting a transform stream back to us, but it works the same both directions. And so on main threads we get the transform stream. So again, we just treat this as a regular transform stream. We fetch our data coming from the network, we pipe it through that transform stream, and we consume the output coming out of it. And what happens on the worker, we don't care. It might eat up all of the CPU of that thread, but main thread will keep being snappy, being very responsive, and keeping everything flowing smoothly. Now, transferable streams are pretty well supported, actually. So Chrome and Firefox, again, Safari, catch up, please. But the good thing is, if you can't wait, you can polyfill all of these features. So again, I maintain the WebStreams polyfill. This has support for async iteration. This has support for readable stream from. And if you want to use transferable stream, the API is a bit different, but I also have an NPM package for that. So there's no reason not to use streams. You can. So go for it. That is all I've got today. Any questions? Yes, Damian. Correct? So there are some Apple engineers that review the spec changes, but right now it is mostly 2 Chrome guys and me. Yeah. It's just, yeah, they support the spec changes, so they review that and they see that they are in agreement with it, that they don't see any like privacy concerns with it or something, or things that they don't want to implement. But it's just, yeah, it has to still go into a development team and be prioritized for them. There are other contributors to WebKit. It's open source these days. It's all on GitHub. So if anyone feels adventurous, they can try to send a pull request to them. That would be very nice too. At some point, they will get some pressure on them, and yeah, back pressure. When the queue reaches the desired size. Yeah. Okay. Yes. No. So the desired size of a stream is something that the stream will say like, okay, I want to apply back pressure, but it's never going to drop a chunk. So even if the stream is applying back pressure, you can still enqueue more data onto it. It'll be a bit sad that you're not respecting back pressure, but it will still keep growing and growing your queue as needed. Yes. Yes. Mm-hmm. So if you can write a transform stream that accepts arbitrary size chunks and then splits them up and then re-enqueues them to the next one in line. So you can write your own stream that does the limiting. So for example, what we at Theo would do is we take in an arbitrary byte stream coming off the network, and we see that it's FMP4, so we would chunk that at MP4 boundaries. And so then the next one in line doesn't have to worry about dealing with half an MP4 file somewhere, for example. Yes. A transform stream would be in the middle there. So a transform stream, all of my examples have been just calling enqueue once in transform, but there is nothing stopping you from calling enqueue multiple times. Mm-hmm. No, you get every chunk individually, yes. There is no API to say I want to read the entire queue all at once. You would have to repeatedly call read to get that, yes. Yes. There is currently no API to see if there are, yeah, so you would say like, okay, you're in the reader, you want to know if reader.read is going to do actual awaiting or if it's just going to read from a queue. There is no API to introspect that at this point, no. But it is something that I've also thought about, like maybe that would be cool to have, but yeah, we need a proper use case to support why we would want an API for this. Again, the stream standard is up on GitHub. Last link there, slides will go live. I'll put a link to the slides on Meetup too, so you can look at it. But this is open. All of the web standards are developed in the open. So if you have a good idea and you can get some support of it, you put in some effort, you can get this into the spec. Okay, I think that's all.